Welcome back to The Deep Dive, the show that takes a complex stack of sources, the articles, the research, the internal notes,
Yeah.
and extracts the absolute critical intelligence you need to be instantly well-informed. Okay, let's just jump right into this core tension. If you're a developer or an architect or a security leader, you know this feeling. It's that sudden cold dread. It's maybe 3 in the morning, and you realize you might have committed a critical secret credential,
Oh, yeah.
an API key, maybe a database connection string, into a public or even a semi-public repository.
That is a gut punch moment.
It is. That feeling of, oh no, did I just expose the entire company? That feeling is really the central tension of modern software development.
It is because the speed of development has just exploded.
Completely. With continuous integration, continuous delivery, microservices,
Yeah.
it's all moving so fast that those, traditional late-stage security reviews, they've been totally outpaced.
They can't keep up. Every single rapid deployment becomes a potential supply chain vulnerability.
Exactly. So our mission today is to cut through that anxiety. We want to give you a comprehensive shortcut to understanding the modern solution, which is embedding continuous security early. The industry calls it the shift left security mandate. We've been digging into a huge stack of source material here, all focused on Microsoft's integrated security stack. We're talking specifically about GitHub Advanced Security, Defender for Cloud, and Sentinel. And we're going to walk you through a detailed and, frankly, a jaw-dropping real-world case study. A cloud honeynet that was built specifically to lure and track attackers in a live Azure environment.
And, the stakes for getting this right are just enormous. It goes way beyond the security team. This hits the business bottom line directly. You mentioned that feeling of dread, but let's put some numbers to it. Our sources, they stress this over and over again. Fixing a security bug in the initial design phase can be up to 30 times cheaper than waiting until the application is already out in production.
30 times. That is a staggering number. So why is it so much higher? Is it just the engineering time to refactor everything, or is there some kind of, cultural cost to stopping a production rollout?
It's really a combination of both, and that's why the number is so high. I mean, think about it. If you find a flaw during design or even development,
Right.
it might take a developer a few hours to fix that one component. But if you find it in production,
It's a crisis.
it's a full-blown crisis. You have the immediate cost of incident response, the triage, the communication, the forensics. Then you have the engineering cost of refactoring a live interdependent system that can touch multiple teams. And more subtly, there's that huge cultural cost of these high-stress emergency deployments, and you lose trust from stakeholders. So that 30x figure, it really captures the full disruptive life cycle of fixing something late.
Okay, that makes sense.
And if that financial justification wasn't enough, just look at the regulatory and competitive pressure. The average cost of non-compliance for an organization is a staggering $14.82 million annually. And that threat vector we talked about, supply chain attacks where vulnerabilities get injected through third-party components or compromised artifacts, that increased by 633% between 2020 and 2021 alone.
633%.
I mean, that velocity means security isn't some optional add-on anymore. It is a fundamental, non-negotiable cost of doing business and maintaining trust.
That is the perfect foundation for what we're building on. This deep dive is going to show you exactly how the best organizations are managing that cost and keeping up that required velocity. So here's our roadmap. We're going to start with the foundational philosophy, the shift left mandate, and the specific tools that enable it, GitHub Advanced Security, or GHAS. Then we'll pivot to what we're calling the Security Watchtower. We'll look at how Microsoft Defender for Cloud and Sentinel give you that crucial runtime visibility and correlation. Next, we're going to spend a good amount of time walking through the specific controls you need for securing the full software development lifecycle phase by phase. And finally, we will wrap up with that incredible data-rich honeynet case study showing the quantifiable results of building these integrated security controls into your cloud environment.
Okay, let's start where the rubber meets the road, the source code. We hear shift left all the time, but like we said, it's so much more than a buzzword. It's a complete philosophical shift.
It is. It's moving away from bolt-on security to security that is truly baked in.
The old way was, the security team acts as these gatekeepers. They run a pen test right before you go live, and then they force developers to drop everything to fix some last-minute crisis.
Which nobody enjoys.
Nobody. Shift left is about Integrating those security checks, compliance, vulnerability assessment, threat mitigation from the very beginning, from the design phase all the way through the entire SDLC. It makes the developer the first line of defense. You give them immediate feedback, not some punitive report weeks after the fact.
And the mechanism that really enables this, especially for organizations in that Azure and GitHub ecosystem, is GitHub Advanced Security, or GHAS. Our sources position it as this comprehensive native toolset that brings professional security controls right into the repository, into the developer's workflow. So what are these three big integrated pillars that define GHAS?
GHAS is basically made up of three primary automated pillars, and they all operate directly on the source code and the repository history to stop those common high-impact vulnerabilities before they can even get to the CI/CD pipeline.
Okay, so let's dive deep into that first pillar. This feels like the engine room of proactive security. Code scanning, using CodeQL. This is the modern take on static application security testing, or SAST.
Yeah, and CodeQL is a huge paradigm shift in SAST. Traditional SAST, it often just relied on basic pattern matching or regular expressions.
And those were so noisy, right? Tons of false positives.
Exactly. They were noisy, they produced way too many false positives, and they really struggled with vulnerabilities where the data flow was complex, spread across multiple functions.
So if a vulnerability was subtle like, maybe tainted user input gets sanitized in one function, but then it's mistakenly passed to a secondary insecure function like 10 steps later, a traditional scanner might totally miss that flow.
Precisely. And CodeQL solves this by treating your source code not as a bunch of text files, but as a fully queryable relational database.
That database.
Okay. Yeah, this means CodeQL builds this comprehensive hierarchical model of the entire code base. We're talking the abstract syntax tree, the control flow graph, the data flow graph. And then it allows security researchers to write these incredibly sophisticated, specialized queries against that model.
So instead of just looking for a keyword.
Right. Instead of that, the query asks a much smarter question. It asks, show me all locations where user-controlled input, the source, which has not passed through a validated sanitization function, ultimately reaches a high-risk operation, the sink.
Like a database query or a file system, right?
Exactly. This is deep data flow analysis that can reliably detect entire classes of vulnerabilities like SQL injection, cross-site scripting, command injection, and it supports a ton of languages: C#, Java, JavaScript, Python, C++, Sysips.
That relational database approach means you can analyze huge, even decades-old code bases with real consistency. But crucially, where does the developer see the output from all this?
The results are immediately integrated right into the developer's native tools. They see it in the Azure DevOps UI or right there in the pull request interface. They're often delivered in a standardized format called SARIF. That's the Static Analysis Results Interchange format.
SARIF. Why is a standard format like that so important?
It's important because it's like a universal language for security findings. It makes the output from CodeQL consumable by other tools in the ecosystem, and it makes sure the alert shows up exactly where the developer needs to see it before they merge the code. That immediacy is what makes shift left actually work day to day.
Okay, that's powerful. Let's move to Pillar 2, which addresses that 3 a.m. panic we talked about: secret scanning and push protection. This feels like a critical defense against immediate, high-impact exposure.
It really is. Secret scanning is designed to prevent the accidental committing of sensitive credentials, API keys, tokens, SSH keys, certificates into the repository history.
Where they can get scraped by bots almost instantly.
Instantly. And the scope here is massive. The tool scans for over 200 token types and supports more than 180 service providers. And that signature library is constantly being updated.
That huge scope is vital. An attacker doesn't care if it's an AWS key or an Azure storage key. Either one is a critical exposure. But the real game changer here seems to be the push protection feature. Why is catching the secret at commit time so different from a post-push scan?
Because when a secret is exposed, even for just a few minutes, you have to assume it's compromised. There are bots that do nothing but scrape public repositories for these patterns 204/7.
So a post-push scan is already too late? You're in damage control mode?
You're already in damage control. You're revoking keys, checking for usage. Push protection intercepts the commit before it's written to the remote repository. The tool tells the developer exactly why the commit failed, like Azure storage key detected, and it blocks the commit entirely. This just saves the entire team that frantic, expensive, and super stressful scramble of revoking and rotating a compromised key. That is a massive administrative headache. It transforms secret management from this reactive cleanup job into a proactive, enforced policy right at the source.
Absolutely. Okay, and that brings us to Pillar 3, which tackles the unseen complexity of modern development. Dependency scanning, or software composition analysis, SCA. This is all about the software supply chain.
Right. I mean, every modern application relies on dozens, if not hundreds, of open source components, frameworks, and libraries. This is great for development speed, but it introduces a ton of third-party risk. Dependency scanning identifies those vulnerable components by continuously analyzing the manifest files, things like your package.json or pom.xml.
So it looks at all the stuff you pulled in and then checks it against a giant database of known bad actors.
Precisely. It scans those dependencies against these massive centralized advisories, primarily using the GitHub Advisory database, which tracks all the known CVEs, common vulnerabilities, and exposures. And the key component here is a tool called Dependabot.
Dependable.
Yeah. So when a known CVE is detected in a library version you're using, the Dependabot automatically scans for the fix.
This is the automation we love.
It is. Dependabot doesn't just give you a warning. It acts like an automated fix agent. It will create a pull request for you right there in your repository, suggesting the update to the non-vulnerable version of the library.
So all the developer has to do is review the change and merge the PR.
That's it. This hugely reduces your software supply chain risk by automating the fix for known weaknesses. It stops that security debt from piling up.
That makes the whole process scalable, especially for a big organization with hundreds or even thousands of repos. Instead of a security team manually chasing down vulnerability reports, the system just automates the fix and gives it to the developer as a normal code change request. And let's close this part out with that AI accelerator you mentioned. GitHub Copilot being integrated into this process. How does AI speed up remediation here beyond just suggesting code?
The Copilot integration just radically shrinks the time between finding an alert and actually fixing it, the remediation cycle. For those code scanning alerts, the AI-powered autofix agent uses the context of the vulnerability found by CodeQL and suggests the secure coding pattern needed to fix it.
Okay, but it's more than just a suggestion, right?
It is. Here's the deep part. It doesn't just suggest the code, it can also suggest and then validate the remediation. This means it helps the developer confirm that the suggested fix actually solves the security flaw and doesn't break the intended function of the code.
That reduces the cognitive load on the developer tremendously.
It does. When you can shorten remediation cycles from days where a developer has to stop, context switch, research the vulnerability, implement a patch down to just hours or even minutes, you are truly delivering secure velocity.
So the big takeaway here is that GHAS ensures consistent security policy across all your repos. It prevents a single developer's mistake from becoming a systemic breach, and it does it all by integrating the fix right into the development flow itself.
Yeah.
Okay, so we've successfully shifted left. Our GHAS tools are stopping problems at the source, which is great. But what happens the second that code leaves the registry? It gets built into a container image, and suddenly it's running live in an Azure Kubernetes service cluster or on a VM.
Right.
At that point, we need a completely different kind of security visibility.
That's the critical pivot. Shift left manages the input, runtime security has to manage the execution. And this brings us to the two major security platforms in the Azure ecosystem that, frankly, are often confused. Defender for Cloud and Microsoft Sentinel. We need to be really clear about what each one does.
Let's reinforce that analogy we came up with. We called Microsoft Defender for Cloud, the Firefighter, or the Extended Detection and Response Tool, the XDR.
Right, the XDR.
And Microsoft Sentinel is the command center, the SIEM SOAR system.
That analogy holds up really well. Defender is focused on that deep, continuous, real-time protection at the individual workload level, the specific resource. Sentinel, on the other hand, is all about correlation and centralized intelligence across the entire enterprise. It connects the dots between all the alerts generated by Defender and all the other services.
Okay, let's start with the Firefighter then, Microsoft Defender for Cloud. We're talking about XDR, Extended Detection and Response. What does the extended part of that actually mean in terms of protecting a workload?
Well, XDR extends detection and response beyond just a single security layer. Defender for Cloud gives you this unified security posture management and continuous assessment capability across all your cloud resources. Its recommendations are benchmarked against industry standards, like the Microsoft Cloud Security Benchmark, which itself is derived from frameworks like CIS and ISO. The real depth, though, comes from its specialized plans. It's not just one tool, it's a whole suite of integrated specialized defenders. For example, Defender for Servers gives you endpoint detection and response EDR for both Windows and Linux, so it's monitoring process execution, kernel-level activity.
And there's one for storage too, right?
Yep. Defender for Storage detects unusual attempts to access storage accounts. It'll flag things like access from a highly concentrated or unauthorized geolocation that could signal an exploit attempt.
That specialization is so important, especially as cloud environments just get more and more diverse.
Absolutely. You've got Defender for SQL, which protects databases against classic SQL injection, but also behavioral anomalies, like a huge amount of data being exfiltrated suddenly. And then for modern microservices, there's Defender for Containers.
Securing Kubernetes clusters.
Exactly. Checking host configurations, scanning container images in the registry, and providing runtime monitoring of pod activity.
And we touched on the really cutting-edge part of this protection, which speaks to how fast technology is evolving. Defender for AI services. What specific threats is that designed to catch?
This is brand new, and it's so vital. As organizations deploy intelligent agents and large language models, LLMs, through Azure AI, they're facing totally new security risks. Defender for AI services provides runtime protection against things like prompt injection and jailbreaks.
So that's where an attacker manipulates the model's input to try and get it to reveal sensitive data or change how it behaves.
Precisely. It also monitors for suspicious access patterns to the underlying data that feeds the AI, guarding against data exposure during training or inferencing. It's really about protecting the intellectual property and the integrity of the AI model itself.
That is truly comprehensive workload protection. Okay, so now let's move up to the command center. Microsoft Sentinel. If Defender is generating alerts about specific bad behavior on a workload,
then Sentinel is figuring out the grand strategy behind those individual alerts. Sentinel is the cloud-native SIEM security information and event management and SOAR security orchestration, automation, and response solution. Its whole job is centralized intelligence at cloud scale. It pulls in data from everywhere: Defender alerts, Azure activity logs, network flows, identity logs from Entra ID, even multi-cloud environments like AWS and GCP, and other third-party solutions.
the real power, as we noted, is in the correlation. How does Sentinel go beyond just being a giant log bucket?
It uses advanced analytics, powerful machine learning, and especially a technology called User and Entity Behavior Analytics, or UEBA.
UEBA.
Yeah. UEBA creates a baseline profile of what's considered normal behavior for every single user and entity servers, applications in the environment. So when an alert comes in, like a login from an unexpected country, Sentinel compares it to this baseline. For instance, let's say user X always logs in from London during business hours and only accesses application Y. But then suddenly, a login happens from an anonymous IP in Southeast Asia, and is trying to access a totally unrelated storage account.
Even if the credentials were correct.
Right, even with valid credentials, UEBA flags that as high risk. Then it might correlate that with firewall logs that showed brute force attempts earlier that day. It stitches all that together into a single high-fidelity incident, which dramatically minimizes the false positives.
That correlation capability is what justifies the entire SIEM investment. And once it confirms that sophisticated attack chain, the SOAR component, the automated response, kicks in. How do those playbooks work in real time?
The SOAR capability uses playbooks, which are basically automated workflow sequences built on Azure Logic apps. Instead of a human analyst having to wake up, log in, and manually execute containment actions, which can take minutes or hours.
The playbook does it in seconds.
In seconds. A high-fidelity alert might trigger a playbook that automatically isolates the affected VM, blocks the source IP on the Azure firewall, forces a password reset through Entra ID, and at the same time notifies the on-call team via Teams or email. This rapid, deterministic response is essential for containing fast-moving threats like ransomware.
Okay, here's where the ecosystem really shines. The unifying link. The huge gap, historically, was that chasm between the development world and the security operations world. CodeQL alerts stayed with dev. Defender alerts stayed with SecOps.
And now they talk to each other. This is the essence of code-to-cloud traceability. The system performs what's called smart mapping. It automatically tracks the source repository, the specific GitHub or Azure DevOps repo, to the running cloud workloads. It often uses metadata that was injected during the CI/CD deployment process.
So it knows that the container running in AKS cluster A came from repo B.
Exactly.
And what does that smart mapping enable that just radically changes the security team's workflow?
It enables prioritization based on context. A vulnerability found by CodeQL might exist in 50 different repositories. Now, if Defender sees that 48 of those workloads are internal, behind multiple firewalls, but 2 of them are live, Internet-exposed web front-ends handling sensitive data.
Then the alerts for those 2 repos immediately get flagged as critical.
Instantly. Security teams can stop chasing non-exploitable vulnerabilities and focus their limited time and resources on risks that actually matter, because they're dynamically linked to the critical assets in the running environment.
So the security team gets runtime context, and in turn, the developers get the security context.
Precisely. The remediation workflow is completely unified. A security analyst can generate a GitHub issue or an Azure DevOps work item directly from inside Defender for Cloud. And that issue automatically includes the runtime context. It'll say, hey, this SQL injection vulnerability is exploitable because this container is internet-facing, right alongside the CodeQL details. This delivers the fix request to the developer in their native tool, and the system tracks the issue status both ways, ensuring clear accountability and a much faster resolution.
Which is then often accelerated by those Copilot AI fixes we talked about earlier.
It all connects.
Before we move on, let's quickly touch on 2 other critical pieces of the Watchtower: identity and network defense.
Sure. For identity, we rely on Microsoft Entra ID Protection, which is a P2 feature. This is basically the behavioral police for your users. It uses machine learning and heuristics, things like impossible travel between logins or login attempts from known bad IPs to calculate a real-time user risk level.
And based on that risk level, it can enforce conditional access policies.
Exactly.
Yeah.
Like immediately requiring a multi-factor authentication challenge for a suspicious sign-in, or even completely blocking access until that risk is mitigated.
And for network defense.
2 main layers there. You have the Azure Firewall, which is the cloud-native layer 3 through 7 traffic inspection tool. It blocks known malicious traffic, both north-south and east-west. And then complementing that is the Web Application Firewall, or WAF. This often runs on application gateway or front door, and it's focused specifically on protecting web applications against the infamous OWASP POP10 list. It'll prevent SQL injection, cross-site scripting, and other web exploits before they can even hit your application server.
That is a seriously comprehensive Watchtower framework. It really shows how threat prevention with GHAS, workload detection with Defender, and centralized correlation with Sentinel all combine to give you that full coverage. We've covered the philosophy, the integrated toolset, and the runtime visibility. Now let's get into the mechanics. How do you actually turn this DevSecOps vision into a set of repeatable, enforceable daily practices?
Right.
Our sources lay out a really valuable framework by aligning specific high-impact security controls with the 5 traditional phases of the SDLC.
And this step-by-step structure is crucial. It ensures security isn't just some audit point you check off at the end. It becomes a true part of the software pipeline.
It forces teams to put controls in at the exact moment they're easiest and cheapest to implement.
Exactly. It directly addresses that 30x cost disparity we talked about at the start.
Okay, let's begin at the very start. Phase 1, the plan phase. This is all about designing security in, making threat modeling systematic and mandatory.
Threat modeling is the non-negotiable first step. It forces security and architecture teams to analyze the design before a single line of code is written. The recommended methodology is the STRIDE mnemonic.
STRIDE.
Yeah, it gives us a structured way to think about threats across the entire system architecture.
Let's quickly remind everyone what STRIDE stands for and why breaking down threats this way is so effective.
Sure. STRIDE stands for spoofing, which is about identity, tampering, data integrity, repudiation, accountability, information disclosure, confidentiality, denial of service availability, and elevation of privilege, authorization. You apply STRIDE to your data flow diagrams, your DFDs, looking at every single process, data store, and data flow.
So for a data flow between 2 services, you have to ask, how could an attacker tamper with that data?
Right. Or does the service have a trust boundary that could be spoofed? Where is sensitive data stored, which could lead to information disclosure? This systematic analysis, which is often helped by the Microsoft Threat Modeling tool, reveals architectural flaws, like a missing authentication layer or an insecure data storage mechanism, long before they become bugs in the code.
And the output of this has to be actionable, right? It can't just be a document that sits on a shelf.
Absolutely not. The identified threats have to be converted directly into Azure DevOps work items, user stories, or tasks with clear ownership and defined mitigation strategies. This acts as a real architecture review gate. If you change the design, you have to trigger a new threat assessment. This pre-development work is the single most effective way to reduce the risk of those late, expensive architectural flaws.
Okay, moving from the design on the whiteboard to the individual developer's keyboard. Phase 2, the develop phase. This is the core of shifting left in the daily coding workflow.
This phase is all about minimizing friction while enforcing secure coding standards. We adopt best practices, often from the OWASP Foundation, covering things like input validation and secure resource access. But the key is immediate feedback. Developers use IDE tools and plugins like SonarLint or Sync, integrated right into VS Code or Visual Studio.
So if a developer types a function that's known to be insecure, or they forget to sanitize an input string,
The tool gives them real-time feedback, a little yellow squiggly line, before they even save the file. This actually teaches secure coding habits and eliminates that need for context switching later on.
and beyond the IDE itself, what about repository controls? How do you lock down the process?
We have to enforce strict repository controls. This means mandatory branching methodologies like GitHub Flow, where direct commits to the main branch are completely prohibited.
Right.
You must require peer review and a minimum number of approvals before any code change can be merged. This ensures at least 2 sets of eyes review the logic.
And what about pre-commit hooks?
Critically, we mandate the use of pre-commit hooks. These are just localized scripts that run on the developer's own machine before the code is even committed. They can be configured to run local scans for secrets, stopping the code from ever leaving the developer's environment if a credential is found. It's another layer reinforcing that push protection we discussed.
It prevents those 3 a.m. panic moments.
Yeah.
We also need to think about the artifacts being created here, especially containers.
Yes, for sure. When developers are building containerized applications, they should consciously select lightweight, minimal base images.
Like Alpine or Distroless.
Exactly. Using images like Alpine, Distroless, or Mariner dramatically reduces the attack surface compared to a full OS image. Fewer components just means fewer vulnerabilities that need patching, and a smaller payload to scan in the first place.
Okay, now we hit phase 3. The build phase. This is where the continuous integration pipelines run, and we scan everything that's going into the final artifact.
This is the automation hub. We integrate comprehensive SaaS-like CodeQL into every single build. And if a high-severity vulnerability is found, the build must fail. It's a hard gate that prevents insecure code from moving downstream. But we also need to scan the infrastructure definition itself. We use infrastructure as code or IAC scanning tools, something like Checkoff.
And that looks at your Terraform or Bicep files.
Exactly. It proactively monitors those cloud resource configurations. It can ensure, for example, that an S3 bucket or an Azure storage account isn't accidentally defined as public before it's even deployed. We also use tools like KubeScore to validate Kubernetes deployment objects for security best practices, minimizing those cloud misconfigurations that lead to so many breaches.
This phase also involves establishing the integrity of our container images. This is where signing and verification come in.
This is a complex but absolutely vital control layer. It protects against software supply chain attacks, specifically image substitution attacks. We need integrity assurance. We use tools like Notation, which is integrated with services like Azure Key Vault to store the cryptographic signing key. When a container image passes all its security scans in the build pipeline, it gets digitally signed.
And then something has to check that signature at deployment time.
Exactly. In the deployment environment, we use enforcement tools like Ratify and AKS. Ratify acts as a gatekeeper. It checks the digital signature on the image before it allows the container to start. If the signature is missing or it's invalid or doesn't match the trusted key in Key Vault, Ratify just refuses to pull the image. This ensures that only verified, untampered artifacts that successfully pass the security pipeline are allowed to run in production.
That is a fundamental security boundary. If you can't verify the origin and integrity, it simply doesn't run. Let's move to phase 4, the deploy phase. These are the last-minute quality and authorization gates.
This is the perfect spot for dynamic application security testing, or DAST. SAST, which was CodeQL, scanned the source code. DAST scans the running application in a staging environment that mirrors production.
So tools like OWASP-ZAB or Burp Suite.
Right. They actively probe the deployed application, and they find configuration weaknesses, authentication flaws, authorization bypasses, and API security gaps that static analysis just can't see because they depend on the runtime environment. And we must also implement robust pipeline control. Before deploying to production, we require approvals and gates. This often means a manual approval from a security team, or maybe a minimum standard being met, like the DAST report shows 0 critical findings.
And what about eliminating the credentials problem in the CI/CD pipeline itself? That's always a weak spot.
It's crucial. We have to eliminate the need to store long-lived credentials, like service principal secrets, in external CI tooling. We can do this by using methods like OpenID Connect OIDC or by adopting a GitOps pull-based approach. OIDC lets the CI pipeline dynamically request a short-lived token from Entra ID based on workload identity federation. It provides just enough permission for the deployment to happen, and then it expires immediately. No secrets are stored, which drastically reduces the blast radius if the CI/CD environment is ever compromised.
That significantly hardens the weakest link in so many pipelines. Finally, we reach phase 5, the operate phase. The application is live. Now we have to ensure continuous monitoring and governance.
This is the continuous health check. Defender for Cloud takes over posture management here. It's performing continual scanning for configuration drift, vulnerability state changes, and compliance issues against your security baseline. It'll detect if a container that was signed and verified suddenly starts running a privileged process, for instance.
And for governance.
For governance, we use Azure Policy. And we can extend Azure Policy using open source tools like Gatekeepers to secure and govern our AKS clusters at admission time. This can prevent high-risk deployments from ever succeeding, for example, ensuring that no container can run as root or that images are only pulled from trusted, verified registries. It reinforces that ratify control.
And how do we make sure the security team actually sees all this operational activity?
We implement centralized monitoring. We do this by forwarding all of the DevOps audit logs, pipeline changes, deployment activity, access to sensitive configs via Azure DevOps audit streaming directly to Microsoft Sentinel. This lets the SOC team correlate DevOps activity with network, identity, and application logs. So if Sentinel sees a suspicious user login from Entra ID and then immediately sees an unapproved pipeline deployment in the DevOps logs,
That's a high-fidelity sign of a compromised account targeting the infrastructure.
a huge red flag.
So the STLC is now this seamless, enforceable loop. Security decisions made at the planning table are continuously validated and monitored all the way through to live production. Theory and tooling are essential, but, the ultimate proof is in the real-world application. This final section uses a detailed Azure HoneyNet case study to show the practical, quantifiable results of implementing a robust SOC and incident response framework.
This case study is so compelling because it moves the whole discussion from hypothetical threats to hard, measurable data. It validates exactly why continuous security, driven by platforms like Sentinel and Defender, is absolutely mandatory for any publicly exposed cloud resources.
Okay, let's start with the preparation phase. Can you describe the meticulous setup of this decoy network in Azure?
Sure. The analyst created a multi-endpoint HoneyNet that was specifically designed to attract and analyze attacker behavior. It included a Windows virtual machine, a Linux virtual machine, and a running Microsoft SQL Server database on the Windows VM.
So diversity of targets?
Exactly. To capture attacks targeting common enterprise operating systems and high-value applications. But the critical design element, what makes it a HoneyNet, was the intentional vulnerability.
They deliberately bypassed all best practices.
Completely. They removed the default inbound RDP and SSH rules and replaced them with an allow any traffic rule on the network security groups, the NSGs. On top of that, they disabled the local Windows firewall on the VM itself.
So they basically put up a flashing neon sign saying, "We are wide open."
Pretty much. And while that trap was being set, they prepared the SOC infrastructure, the Watchtower, to capture every single probe.
Right.
All the logs were aggregated into a log analytics workspace, which then fed into Microsoft Sentinel for that centralized intelligence. But they went a step further in preparation. They uploaded a massive GeoIP watch list. It had over 50,000 rows of geolocation data directly into Sentinel.
So they could visualize attacker origins immediately.
Instantly. For every SSH, RDP, and SQL attempt. And finally, they defined specific Sentinel analytics rules. For instance, they defined a brute force attempt as 10 or more failed logins from a single IP address within a 1-hour window. They were ready for the inevitable automated storm.
And how long did it take for that storm to hit? Let's move to the detection and analysis phase. What was the volume of data they collected in just the initial 24-hour window?
The sheer velocity of the automated attacks was just staggering. In only 24 hours of being exposed, the system recorded 42,754 Windows security events and 3,636 Linux syslog entries.
Wow.
Sentinel aggregated all of those events into 117 incidents, which it then condensed down to 38 unique open incidents that needed attention. But the most dramatic number was the network traffic. traffic. They recorded 35,805 NSG inbound malicious flows allowed into the network.
You have 35,805 malicious flows allowed in one day. That number is just proof positive that leaving anything unprotected in the cloud is like leaving your front door wide open in a blizzard of automated attacks.
It is. This wasn't targeted human hacking. This was relentless machine-driven probing.
Just bots scanning the internet.
Relentless bots. And the GeoIP watch list confirmed it. The attack maps showed this continuous global concentrated brute force attempt hitting RDP, SSH, and the SQL Server from all over the world. The decoy worked immediately.
Let's focus on the most detailed finding, that deep dive incident targeting the MS SQL Server database. What did the analysis reveal about that specific attacker's persistence?
This was classified as a high-confidence true positive of medium severity. An attacker, geolocating from China, launched this massive, focused brute force attack. They executed 1,832 unauthorized access attempts in just 17 minutes.
1,800 attempts in 17 minutes.
Yeah. They systematically tried 16 different usernames, but they overwhelmingly relied on the predictable default system admin account, SOAR, for 99% of those attempts. This incident just highlights the importance of strong passwords and changing default configurations.
So once that detection confirmed a critical ongoing threat, the analysts moved quickly to the containment, eradication, and recovery phase, the security hardening actions.
Correct. The immediate first step was containment. They locked down those original overexposed NSGs to accept traffic from only the analyst's personal trusted IP address. That immediately slammed the door on all that automated external traffic.
And then they implemented a defense-in-depth strategy.
They did. They implemented systematic hardening measures for comprehensive protection. First, they re-enabled the local Windows firewall, creating another filtering layer right at the host level. Second, they added a new network security group at the subnet level, creating a layered network control. And crucially, they secured the configuration secrets. They added private endpoints to the key vault and the blob storage resources. This restricts access to those sensitive data stores to the private Azure network only. It ensures that even if a VM is compromised, the sensitive backend data is not publicly reachable from the internet.
That's a fundamental security architecture change, moving from public exposure to internal controlled access. So the big question, what was the quantifiable result? What was the outcome in the next 24 hours after this hardening was implemented?
The results were immediate and just absolute proof of concept for proactive defense. Over the next 24 hours, they recorded a 100% decrease in Sentinel incidents. 0 incidents were open.
100%.
They saw a 99.97% decrease in Linux authentication events, just a single log entry. And critically, a 100% decrease in malicious traffic allowed through the network security groups. The automated attacks were entirely stopped.
That is the compelling evidence. The system wasn't just quieter, the security controls demonstrably deflected that continuous automated threat.
The lesson here is just so foundational. Proactively securing your network access controls like NSGs and firewalls, dramatically reducing the attack surface with private endpoints for sensitive data, enforcing strong authentication, and maintaining continuous monitoring with something like Sentinel. These are the non-negotiable requirements to operate securely in the modern cloud.
What an extensive deep dive. We started with the foundational necessity of shift left and the tooling that enables it, GHAzDO, with its pillars of CodeQL for SaaS, Dependabot for supply chain scanning, and push protection for credentials. Then we moved to the holistic visibility provided by our Watchtower, Defender for cloud for that workload level XDR, and Sentinel for centralized SIEM SOAR correlation and automated response.
And the core lesson is so clear. Integrating security early in the SDLC and using platforms that actually talk to each other, providing that crucial code-to-cloud traceability, is what enables compliant velocity. Continuous monitoring and automation, driven by Azure policies, Sentinel's analytics rules, and automated scanning, these are the mechanisms that allow teams to consistently meet strict compliance requirements for frameworks like ISO 27001 and SOS2. When security policy is translated into automated enforceable code and continuous checks, it just becomes routine. It's not a catastrophe, and it simplifies those difficult audits.
Let's leave you with this final provocative thought. It comes directly from the stark data of that honeynet. That decoy network was designed to be compromised, and it was immediately flooded with over 35,000 malicious flows allowed in a single day. That was followed by nearly 2,000 brute force attempts in just 17 minutes. So if systems that are intentionally left wide open are attacked this frequently, you have to seriously consider what level of unauthorized probing, automated brute force, and anomalous activity is currently hitting your own production systems right now. If you don't have a centralized SOC solution like Sentinel or Defender for Cloud, actively collecting, correlating, and analyzing those flows, your ability to focus on innovation rests entirely on your ability to see and enforce your security boundaries. The security you don't track, the policy you don't enforce, is the security you simply do not have.
Food for thought indeed. Thank you for joining us for this deep dive.
We'll catch you next time.